Okay, welcome back to Human Biology. Today's lecture is on science as a way of knowing. So as part of today's lecture, we're going to tackle 4 different topics. First of all, we're going to talk about what is science, what makes science science. We're also going to talk about the different scientific disciplines such as geology, biology, chemistry, etc. And we're going to spend some time talking about the scientific method, which you've probably heard about before in school, but we're going to expand on that and talk about the different parts. And finally, we're going to end up talking about the differences between hypotheses, theories, and laws, because these are terms that have slightly different meanings in the science realm than they do in everyday life. Okay, so let's start out first by talking about what is science. You've heard about science before on TV, forensic science, social science, natural sciences, biological science. So what is science and what makes it science? So there's different dictionary definitions of science. One is pretty boring, an area of study that deals with the natural world. Well, that would be natural science. And if you go down to number 3, I like it a little bit better, a distinctive way of knowing or gaining knowledge about the natural world that starts with a question and then goes to an answer that question using evidence and logic. And number 4 is probably my favorite. Science is a process which uses experimentation, evidence, and logic to continuously test and revise ideas. And over time, through repeated study and repeated experimentation, scientific knowledge advances. This is a very good, robust definition of science. Science is not static. It's not one thing that we learn today and then put that away forever. We're always testing and revising ideas in science. Okay, mostly what we're going to talk about in this course is natural sciences. Natural sciences are the sciences such as biology, chemistry, geology that deal with natural phenomena in the natural world. So if we're thinking about the physical sciences such as geology or the biological sciences, those are all natural sciences. So what is not a natural science? Well, there's social sciences, right? You've heard about that before. So social sciences are a branch of science devoted to the study of societies and the relationships among individuals, that is, people, within those societies. So examples of social sciences include sociology, psychology, political science, those type of things. Linguistics are all social sciences, and they're great. I'm not saying they're bad sciences, but they're not natural sciences, so we're not going to talk about them today. So here are some examples of natural science disciplines. And we tend to put those into 2 different categories, though they blend over a little bit. The physical sciences are over on this side right here, and they are things like chemistry, astronomy, geology, aerospace, engineering. They deal with things that aren't living. And then we have the life sciences or biological sciences such as botany and zoology, marine biology. These all deal with living things. Okay, so you probably have already had biology, at least in high school. You know that biology is the study of living organisms. You learn about cells and tissues and great things like that. And you study embryology and then maybe even a little evolution and things like that. And then we have physics. Physics is a physical science. It deals with the laws governing the natural universe, such as gravity, acceleration, entropy. All those different things fall into the realm of physics. And of course we have astronomy, which is a great physical science. In fact, I'm going out tonight to watch the Neowise comet for the last time. So astronomy is the study of interstellar bodies, galaxies, planets, stars, things like that. So really cool different sciences here. And of course we have meteorology, which is also a physical science. And that's the study of the weather and what causes the weather. That is ocean currents, air waves, things like that. And finally, we have geology. Geology is probably one of my favorite physical sciences. It's not just a study of rocks. If you watch The Big Bang Theory, you hear Sheldon Cooper continuously malign geology. But geology is really cool because we've learned a lot about evolution and biology through geology, because rocks, especially sedimentary rocks, make excellent preservation of biological organisms over time. So we've learned a lot biologically by what's going on geologically. And of course, geology is also looking at erosion and building of mountains and things like that. So really cool science. Okay, and finally chemistry. Now chemistry is something that, even though it's a physical science, it's really going to apply to biology as well. So when we're talking about chemistry, we're talking about acid-base balance, the pH scale, the properties of different elements and how those elements form compounds. So although I've shown you each of these physical and biological sciences by themselves, they really do interact, especially in biology. It draws upon chemistry, it draws upon physics, and so we can't learn biology without learning a little bit of these sciences as well. Okay, so just so you know, we have these two categories, physical sciences, biological sciences. A lot of the cool stuff going on now in science is really going on in between. For example, biochemistry is looking at the chemistry in cells and biological organisms to figure out how metabolism works. Right now we're looking at biochemistry to figure out how to combat this COVID virus by generating antibodies or generating a vaccine. We have biophysics, bioengineering, lots of different cool things going on in between the physical and biological sciences. Okay, now we're going to talk a little bit about characteristics of scientific explanations. And here we're only concentrating on the natural sciences. So in order for us to make a scientific explanation, we have to make a few assumptions. First of all, that explanation has to be based on observations. Now these could be observations with your eyes or your ears or using a microscope, but it has to be some observation that somebody else can make the same observation. In science, we are rational. We come up with rational explanations for certain phenomena. We don't invoke supernatural ones. We don't say, oh, you know, it was aliens or it was ghosts or anything like that. And most of our scientific explanations, all of them, have to be consistent with natural laws, and most of them have to be consistent with theories, although sometimes we do spin a theory a little bit and challenge that theory. But for the most part, we're not going to debunk gravity to come up with a scientific explanation. And finally, we have to utilize a natural cause and effect. Nothing supernatural is assumed to be going on in science. We could be wrong, but that's just the way that natural sciences work. Okay, what are the limitations of natural science? First of all, we can only study natural phenomenon. We're not concerned with ghosts or angels or anything like that. We don't use Ouija boards. We cannot confirm or refute supernatural explanations. So people get a little bit uptight about religion and science and say, well, you know, science says God is dead and things like that. Science really doesn't say that. Science has kind of left that alone because that's outside our realm of expertise or what we can even test. So don't worry about that. Science is not worried about supernatural phenomena. Okay, science, and this is a scary part, in itself does not necessarily make moral decisions. And this can sometimes be bad. You saw Jurassic Park, where the guy had figured out how to clone dinosaurs using dinosaur DNA combined with frog DNA. And at one point, the character stands up and says, well, you spent all this time figuring out if you could do it, you didn't think about whether you should. And again, scientists by themselves, science by itself doesn't make moral decisions, but now we do have different groups of reviewing bodies that make sure that what we do as scientists is moral and is for the betterment of humankind. And finally, the big thing here about science is it does not produce absolute and final truths. All scientific explanations are subject to revision. And that's not to say we're always debunking our hypotheses and theories and things like that. The ones that stand up over time are the ones we hold the most water for, but we're always open to retesting a theory or retesting a hypothesis with new information. So scientists are always willing to be speculative and test something again. Okay, in order to think like a scientist, you need to basically invoke these following assumptions. One, that you can understand nature through systematic study. And again, that can be studied just by looking at a leaf or something like that, or something like looking through a microscope. So these are all ways of making observations. Okay, scientific data, again, there it is, are open to revision. We're able to revise our scientific ideas, and that is okay. But the sound scientific ideas, the ones that really hold up, are the ones that stand the test of time. Think about evolution, okay? Evolution was proposed by Darwin and others in the 1850s, and we've been testing that for over 150 years now, and we still believe in the theory of evolution. So that's a pretty strong theory. And finally, science cannot provide answers to all questions. There's some questions that just can't be answered by science. Okay, now that we know about the assumptions of natural sciences and scientific explanations, we're going to go through the scientific method. And I know at this part you're like, oh gosh, I've already had the scientific method in Miss So-and-so's class and we already talked about it, but we're going to go through it again because it's a very cardinal rule of science. A very important part of how we do science is using the scientific method. So the scientific method is a way to objectively answer scientific questions. And it uses two different types of reasoning. One is deductive reasoning. So deductive goes from very general to specific. And in this case, we're going to go from a hypothesis, a prediction, collecting some data, testing that hypothesis, coming out with an analysis, and then a conclusion. On the other hand, inductive reasoning goes from specific to general. We make a specific observation, and then from that specific observation, we form a hypothesis that governs more things, and then we're able to test that hypothesis through a different type of experiment. Okay, so here are the 6 steps of the scientific method. Depending on which textbook you're using, you'll have 7 or 9 or 8, but there's some steps that are always the same. First of all, we always start out with making an observation. Okay, an observation suggests what questions we might want to investigate and test. So we come up with an observation, and then given that observation, we come up with a question. For example, you might come up with the observation that I don't feel really well today. And that would lead to the question, why don't I feel well today? You might have a hypothesis. One, you might say, well, I had a lot of alcohol to drink last night, so that's probably why I'm feeling very crappy. Or you might say, gosh, I was hanging out with a bunch of people in the last couple weeks, and who knows if they've been social distancing. I wonder if I have COVID. So your hypothesis could be that you have the COVID virus. In this case, a hypothesis here is a tentative scientific explanation that attempts to answer a question about natural phenomenon. Now, you've often heard a hypothesis called an educated guess, and that's, I guess, technically correct, but just keep in mind that it doesn't even have to be that educated. A hypothesis is really just a prediction based on some observations we've made, but keep in mind that a lot of times hypotheses are proved wrong, so don't feel bad if you come out with a hypothesis that is incorrect. It still helps us to narrow down the possibilities and hopefully eventually get to the right answer. The next step of the scientific method is to conduct an experiment. An experiment is a process of testing a hypothesis or prediction by gathering data under controlled circumstances or controlled conditions. Controlled being the optimal word here. Now, in our first example we gave about and said your observation was you didn't feel good, your question was, do I have the COVID virus? In this type of experiment would be simply to go to your doctor and get tested. Very simply like that. Now, let's shift directions and talk about the COVID virus and ways that we might treat it. Well, one way that we all know we might be able to combat the COVID virus is through vaccinations. So there's lots of sample vaccines that are being tested at different stages around the country and around the world right now. So we want to find out, let's say, if this vaccine works. In this case, we want to divide people into a control and an experimental group. Now, the control group is going to get a sham vaccination. That is, they're going to get something they think is a vaccination, but is just saline or something like that. The experimental group is going to get the actual experimental vaccination. So why do we do this here? Why do we have two different groups? Well, there is something called the placebo effect. If people think they are getting a treatment, sometimes they get better anyway. And we're also trying to minimize and eliminate bias as much as possible so that the scientists and doctors that are making these observations of our patients can legitimately state whether or not their vaccine has had an effect on people not getting the virus or reducing the amount of time they have the virus, etc. Okay. In the scientific method, we also need to talk about the types of variables we're collecting. So a variable is something that we can manipulate. So the dependent variable is the outcome variable, whereas the independent variable is what we manipulate. So the independent variable in this case is whether or not they get the vaccine or the placebo. The dependent variable here would be the data that we collect. So if we're doing a vaccination trial and we vaccinate, let's say, 1,000 people and give 1,000 people a placebo, we're going to watch those people for the next 6 or 12 months and see what proportion of them come down with the coronavirus. If 60% in the control group get the coronavirus and only 20% in the treatment group get the coronavirus, then it's a pretty good indication that that vaccine might be at least partially effective. Okay, there's also confounding factors in any experiment that we have to consider. Confounding factors such as age, gender, whether or not they smoke, whether they have hypertension. So all these things can affect our outcomes. And it can result in biased sampling if we're not very careful. So we want to reduce bias because bias can lead to erroneous or incorrect results. And probably the easiest way that we minimize bias in scientific experiments is through randomization. Basically, we get a group of 2,000 people and we randomly assign them to the treatment and control group. We don't just go eeny, meeny, miny, mo, but we actually give them a random number table and decide who's in the treatment, who's in the control. That's so we're not confounding the experiment with all the different health problems that these people might have. And the next thing is we need to do replication. We want a very big study group, not a small one. And that's because if we have a very small study group, let's say 12 children, we could very easily get incorrect results which are not applicable to the population at large. And we'll talk about that in next week's lecture. So, experimental design, sample size, big sample size, good. Little sample size, bad. Okay, so now that we've learned about the first few steps of the scientific method, we're going to go through an exercise where we try to set up an experiment to answer a question. And the question that I'm giving you here is, does aspirin lower blood pressure? So this is a question, and in order to answer that question, I'm going to need a bunch of people. These are our study subjects. Now, do we want a few study subjects or do we want a lot? We want a lot, right? Bigger sample size is better. We also want this group to contain lots of different types of people, different ages within reason, probably no small children, things like that, but also different ethnic groups. So we want it to be a diverse study sample. We're then going to randomly divide the members of that group into 1 or 2 subgroups. So if we had 2,000 people in the study, we're going to put maybe 1,000 in group 1 and 1,000 in group 2. Now, we're going to treat those 2 groups the same except for whether or not they get the treatment variable. So let's say in some studies they actually bring the people in there, they give them the same food, they give them the same things to drink and the same amount of exercise. So we're trying to control for outside or confounding variables. But the one thing they do change is whether or not they get the aspirin. So our treatment group is going to get the aspirin, the control group is going to get a placebo. Placebo here is going to be a pill that looks like aspirin but isn't. And in this case, we're trying to control for the bias that results from the placebo effect. People thinking they're getting a medication that's going to do some good for them, sometimes they actually improve. Now, we're going to observe and make measurements. And the measurements here should be objective. That is, they should be numeric, really, in that case. So we're going to use something called a sphygmomanometer to measure blood pressure in these 2 different groups, probably before and then after they take the aspirin. And it's probably not just a one-time thing. We probably are going to do blood pressure for 2 weeks beforehand, give them a month-long regimen of aspirin, and then measure the blood pressure afterwards as well. Okay. We're then going to compare the results. Okay. If we find out that the blood pressures are the same between treatment and control group, we can say that our aspirin didn't have any effect. If, on the other hand, the blood pressure went up in the aspirin group, we can say that aspirin has a bad effect. It makes blood pressure go up. But if we show that the blood pressure went down in the aspirin group, then we can say that aspirin does truly lower blood pressure. Okay, so we're always going to need to analyze our data to determine whether or not our hypothesis was supported. In this case, it's going to use some graphs, some statistics, things like that. Now, in a human biology class, a 100-level biology class, I'm not holding responsible for p-values and r-squared and statistical methods, but suffice it to say, in order to say whether or not our hypothesis is correct, we have to use lots of math. And finally, based on that analysis, using the statistics and mathematical models, we can draw a conclusion. If, for example, we found out that there was a significant decrease in blood pressure among the aspirin group, we could say aspirin does reduce blood pressure. But if we didn't see any big difference, we can say aspirin does not reduce blood pressure. So the important thing about a hypothesis is oftentimes we're proving them wrong. We never prove a hypothesis right. We can support it, but we don't ever say this hypothesis is proven, but we can disprove it. But even though, let's say we got to this thing and we found out that our hypothesis was incorrect, it gives us another stepping point to start another point in the study. Case in point, years ago they were testing a medication to lower blood pressure in older men. I think they were looking at the 60 to 70 group men, and it was a vasodilator. It's supposed to dilate the blood vessels, which would reduce the blood pressure. They gave it to, let's say, 2,000 men, treatment group, control group, and they compared the blood pressures before and after and found that there was no difference. But at the end of the study, they were debriefing the guys in the group, and these are all elderly men, and getting back the rest of the medication. And in interviewing them and trying to get back the unused medication, they found out that some in the treatment group were reluctant to give it up. And the reason was, when they interviewed them, they found out that men in the treatment group experienced more frequent and longer erections than that they'd been used to in quite a while. As it turns out, even though this drug was no good to treat blood pressure, it was later retested in an experiment and rolled out as Viagra back in the 1990s. So very interesting way of taking one hypothesis that is disproven, but being able to take that medication and test it again and come up with a new use for it. Okay, so given all these sort of hypotheticals, I want you to think about using the scientific method in your everyday life. I'm going to ask you, have you used the scientific method? And you're like, I don't know. Well, the answer is you probably have. Unless you walk around doing random things and expecting random results, you probably have used the scientific method. So let's go through a hypothetical situation. It's time to go to school or go to class. You come outside, you get in your car, and you turn the key and nothing happens. So your observation here is the car won't start. And your question should be, well, why the heck won't the car start? So we've already done the first two parts there. And then you come up with a prediction, and that prediction is called a hypothesis. So what do you think your hypothesis would be if your car's not starting? Well, if you said, you know, maybe the battery's dead. Maybe I left the lights on or something like that. It's an old battery. It's very likely. So this is a very good prediction. And it's based on, you know, knowledge of how batteries work. So you then test the hypothesis. So you don't need a treatment and control group here. We're just talking about a single hypothesis. So in your car, the best way to test this hypothesis is charge the battery, jump the battery, go to your roommate's car, steal their battery, and replace it. And this is doing your experiment. And then you're going to analyze the results. As soon as you put that battery back in the car, you're going to turn the ignition one more time and see what happens. So if the car started after you replace the battery, you can draw the conclusion that, hey, it was the battery that caused my car not to start. The battery was dead. That's why the car didn't start. Unfortunately, I've done this experiment before, and I got down here, and the battery wasn't the factor. I replaced the battery, still didn't start. So then I have to ask, you know, what else is going on? It's the spark plugs, the spark plug wires, all this stuff. The point is that even if you disprove your hypothesis, it will give you a new hypothesis to work upon. You've reduced the number of possibilities, and so then you go back and say, well, what's the next thing after the battery? Is it the starter? Is it the spark plug wires, etc.? So it gives you a new direction to jump off in and do a new experiment. Okay, for the last part of the lecture, we're going to talk about theories, hypotheses, and laws, because these are different types of scientific predictions or explanations, and some have, you know, very little water to them, and some we have a lot of evidence to support them. So first of all, let's talk about a hypothesis. We said before that a hypothesis is simply a prediction, a tentative scientific explanation, or an educated guess that attempts to answer a question asked about the natural world. Our hypothesis for why our car wasn't starting was simply that maybe the battery was dead. So it's very likely that that hypothesis may not be correct, in which case the experiment, the results will cause you to form another hypothesis. Okay. On the other hand, a scientific theory is a widely accepted and well-documented statement that addresses and explains many independent observations and experimental tests. So theories are created from well-tested hypotheses. Think about theories now, and people say the theory of evolution. Evolution basically states that life is related to one another, that complex organisms such as us arose from less complex beings over time through gene mutation and things like that. And a lot of people hear the term evolution, they'll say, well, that's just a theory. Well, the theory in science is different than the theory in everyday life. You having about a theory about who's going to win on the next Big Loser or on a game show, that's really a prediction or a hypothesis. In science, a theory is a very well-tested hypothesis that has stood the test of time. Okay, so theory of evolution is the example here. This is the part of evolution that freaks a lot of people out. We didn't come from no apes. Well, we didn't actually come from apes. We share a common ancestor. Darwin actually didn't really consider apes when he worked on his theory of evolution. He was looking at birds and beak size and things like that. So a lot of times I found out people that have problems with evolution, if you talk about how bacteria evolved, they can deal with that. But if you talk about the man-ape conundrum, they get a little bit defensive. So we're going to try to ease you into evolution towards the end of the semester. But suffice it to say, it is a hypothesis that was tested for over 150 years now. And it's a hypothesis that we've accumulated lots of evidence for. And it's very, very well supported. Okay, next let's go to a natural law. A law is a description or rule of how nature appears to behave. Laws are created from well-supported scientific theories, and they have a small likelihood of being found incorrect. And they're mainly found in physics and chemistry. And the reason is that the prediction that we use in laws always comes out to be the result. Okay? So if I drop this remote control, it's always going to fall to the ground as a result of gravity. So that test will come out of the way 100% of the time. On the other hand, evolution, which is a theory, is a little bit different. Biology is pretty messy, and so we can't always predict how things will evolve given certain environmental circumstances. And so that's why we have it as a theory rather than a law. Okay, but there are laws in biology. There is Mendel's law of inheritance. He basically was a monk that figured out how heritable traits were passed on from pea plant to pea plant. So you had some that had wrinkled pods, and some that had smooth pods, and some that had pink flowers, and some that had white flowers. And when he bred a white flowered plant with a pink flowered plant, he began to realize he could predict the proportion of offspring that would be white or red or pink. And so this led to Mendelian genetics and the laws of inheritance. And finally, we also have Newton's law of gravity, which was, when you drop something, it's going to fall to the ground. So a larger body tends to attract smaller bodies. And that's why when the apple fell from the tree, it hit the earth, which was much, much larger. So the law of gravity is a law because it can be tested, and it always comes out with the same result. And finally, we have laws in physics called the first and second law of thermodynamics, things like entropy and stuff like that. We're not going to get into those, but there are a lot more laws in physics and chemistry relative to biology. So just keep in mind, the lack of laws in biology isn't because biology is a squishy science. It's because that biology oftentimes behaves in ways which are not necessarily 100% predictable. Anyways, I hope you've enjoyed this lecture. If you have any questions, be sure to send me an email or drop me a text. Talk to you later.